Hey there, let's do some theorem proving. So specifically, what we're doing today, what we have over here on the right, is a proof written by a human of some sort of theorem that some people are trying to prove, and they have proven. And recently, Terry Taub posted a video of him formalizing this in Lean, and I thought it'd be interesting to try to do the same thing in Acorn and maybe show off some of the cool features that Acorn has. So this in particular seems like a good fit for Acorn because being relatively new, it doesn't have a huge standard library, but this is a theorem involving universal algebra, which means that all these variables here, the only thing we know about them is that they have this one operation here. And we're just proving something very general. So let's start off. So here I'm running in VS Code. The best way to run Acorn is from within VS Code. And I got a screenshot of this human written proof from the Lean Zulip. And so over here, we're going to write our Acorn code. And in this other tab, we have the Acorn Assistant, which is it's going to tell us stuff from the AI that's built into the Acorn plugin. All right, so let's jump in and get started here. So the first thing we have to do is define the type. So the type here is basically a type class, which means we don't know actually what type these things are. It should apply to anything. I think the magma is anything that has one operation, which we'll call mul here. And it works, just like multiplication. This could be a group, but we actually know nothing at all about it. So the way Acorn works, basically, we type in some stuff, we save, and then, down here at the bottom right, move my face for a second. Whenever you save, it'll run the verifier. So the idea is you write some math, you save, it'll run the verifier, and if you've made any errors, there's basically two types of errors. I'm sure I'll make each of them through here. There's either you wrote something that's syntactically bad, in which case it'll red squiggle it, or you wrote something that's either mathematically invalid or the prover doesn't understand why it's true. You made too big of a jump. And that will show up as a yellow squiggle. So we'll see. Let's type some more stuff and get some squiggles. So the basic point of this theorem is that we have this assumption of this big equation that's going to hold. The main equation, x equals yx sz. So we're going to have to define some of these things. So let's define s as a function. And then of, let's call it zx. And let's see. So szx, we're not going to use this subscript because Acorn doesn't have this sort of subscript. We're just going to make it a regular function. X times z. All right. Save. Great. Syntactically valid. Check. And then we also define this f. So this syntax here is with the angle brackets is saying that this is a generic function that's parameterized on our magma. So f is defined as this thing, x times this stuff. All right. So f we define on some x, y, and f is x times s. All right, cool. And so we have the main equation, which is x equals all this stuff. Let's define the main equation not in terms of s. So this is going to be, this is just a Boolean because it's just something that's true of the class. So you'll notice I have GitHub Copilot here. It's suggesting a bunch of nonsense, but for the most part, we can ignore that. All right, so the main condition is that for all x, y, z, we have this, let's see, so x is equal to y operation x, and then operation, and then I want to put this first, but we haven't defined s yet up here, so I think it should just work for doing this. All right, so does this look right? What the theorem prover can't do for you is prove that you actually copied an equation over from the proof correctly. X equals Okay, cool. All right, we have our definitions. We haven't really proven anything yet. Let's jump into lemma 1. All right, so lemma 1, for any ABC. Okay, so we don't have the we don't have a lemma keyword, so we're gonna have to call it a theorem. So for any three things, so implicit is that we have the main equation and all this. So main being true for M implies the statement of we have here. SBA. All right, so we save it. And you can see immediately this gets yellow squiggled. This is Acorn saying this. We typed it in syntactically, but it's not immediately obvious why this is true. So what we generally do is we keep entering in the intermediate steps. In general, in Acorn, you're not writing tactics per se. You're adding true statements that are the ones you would use to prove this current true statement. And then the actual tactics get inferred by the language itself. So the idea is that this should make things easier because there's stuff that you don't have to do. So let's see. What is the first step here? For x equals SBA and y equals MA. Okay, I think this notation means that y is something operation A. So then we have y. Yeah, so if this is, so if y is ZA, then that'll be like saying we have ZA x equals A. Okay, let's bust this out to be its own theorem. Since these are called lemma, let's call this something else. This is a claim. So here, since we're saying assume y is of the form z times a, let's just write this in terms of z. So we have, let's see, what are the, for all a, b, and then z, the actual statement is y x equals a. So let's see. So y equals za here. Hold on. Y equals za and x equals sba. So what's the actual thing we're trying to prove here? So we have y operation x. All right. So in this human written proof, we just say this for one sentence, yx equals a. And then in the Acorn proof, yeah, Acorn also just gets this immediately. So I don't actually understand why the sentence is true. But the author of this paper understood, and Acorn understood and understands. If I want to get more information, this is where the assistant is useful. I can just click on the thing I don't understand, and then it explains what exactly it's doing. Here's how thing. Okay, it uses the main definition. I use the definition of S, and then it does a rewrite. Okay, it rewrites this thing. All right, good enough. So let's see. So back to the lemma. We still, this isn't enough to prove the lemma. So we want to apply the main equation to get this. So a good strategy of formalizing in general in Acorn is you take the equation, that's the big equation in the middle of the page, and then you type that out and see if Acorn gets it right away. So let's do that here. SBA equals A times S of Z S of BA. Okay. That looks good to me. Here we have a red squiggle. And the problem here is local constant Z not found. Oh, that's right. That's why I wanted to have it be Z times A, because Z is the thing that that you combine. Z is this variable. We're assuming Y equals Z operation A here. Okay. So we need to be explicit here for what the definition is of Z S. Wait, what is Z? Oh no, Z is S of C of B. Great. All right, now everything checks out, and this is sufficient to prove the theorem. Okay, on to lemma 2. For all A, there exists B, C, D, such that, etc., etc. All right. Let's see, for all A, let's see, main M implies exists B, C, D, so that F of BC equals S of DA. All right, cool. So this isn't enough either. So by the definition of F, we have F of BC equals this. All right, to me as a human, this is a little bit weird because we don't know what B is yet. All right, to me, the logical first step would be taking B equals S of XA for some X. All right, so first we want to move that over. We have to say for some X. The syntax here is a little bit janky. You can't just say let X colon M. We have to say what it satisfies, but we don't have anything that we want to satisfy. We just want it to be anything at all. So we can put true. All right, and then we take B equals that stuff. So let B satisfy equals S of XA. Okay. And now we rewrite to find this equation here. All right, this equation here, let's write that over. Oh. No, we haven't defined C either. What is C? I see. C is just anything here. The statement holds for all C as well. Okay, I kind of think it would be simpler than we just put it up here and prove that it's true for all C. All right, yeah, great, that works. Okay, there's lemma 2. Now, let's go on to lemma 3. All right, for all A, there's an E such that SEA equals A. Okay, so for all A, that the main theorem holding implies there exists an E so that S of EA equals A. All right, left multiply the equation of lemma 1 by A cubed. And then the first equality comes from the main equation. So let's see. So we want to prove this, but what are B and C here? Take B, C, D as in lemma 2. So they're just anything? Let's try. We can change it later. All right, so we have this lemma 2, and lemma 2 is this thing. F of BC equals S of DA. Okay, we can find such BCD. Great. All right, and so what do we want to left multiply? Now that we have BC and D, we can write this thing we want here. We want A is equal to, this first thing is A cubed. And then we operate it by SBA. Great. Yeah, so you can see these little check marks. When I save and then a little check mark appear, that's Acorn saying, yes, this is valid. This checks out. Okay, and so this is the first equality, and then we need that second one. We want that A equals this thing. Oops. So this is A cubed. And then we operate by A operation FBC. Great, that makes sense as well. Okay. Now we're back here. Take BCD as in lemma 2 to rewrite this stuff. All right, so the next big theorem we have to prove, or the next statement we want to prove is this thing. A operation FBC equals A operation SDA. Okay, and then we want this same left-hand side to also be equal to FAD. On the other hand, lemma 1 with A equals B and C replaced by D implies this thing. Okay, so this is the next conclusion. A cubed all right, great. And that's good enough to prove lemma 3. All right. Last step. For any A and Y using the notation E, we get this thing. Using the notation E. Okay, so that's like for any A and Y, there exists some E such that this stuff, and then we insert this to give ZYA equals Y. Okay, so let's see. So we want so let's see. So for any A and Y, and M implies this A equals SAY equals SAY. Wait, that doesn't make sense. This is weird because I wrote using the notation E and then I just wrote A equals SAY. So there's kind of an unused exists E thing here. Well, okay, this still checks out, right? Yeah. All right, well, this is good enough. What's the next claim in this proof? For any A, Y, Z, and M implies zy a equals y. Yeah, that sounds good. All right. Thus, well, the conclusion of here is thus the ultimate goal is to prove that this whole thing has to be a singleton, i.e. there's only one element. So x, m implies x equals y. And then, yeah. All right, here we are. So yeah, we have this Acorn proof. It took us, I don't know, I'll have to check to see how long it took. And you know, the nice thing about this is all pretty straightforward. I didn't have to use any tactics, essentially. Just taking expressions that were partway steps to the proof and entering them as steps in the Acorn proof here. I honestly think that eventually, and probably even before too long in the future, we're going to have AI systems that are able to do this. Claude Code, for example, everything I did here is pretty routine, and you know, there's a bunch of steps of me running into errors and resolving them, but they're pretty straightforward. So to go from PDF to formally verified proof, I think we're pretty close. I think this is going to happen. And here I didn't use, I mean, I had GitHub Copilot on, but I don't think I used it a single time. What is being used in AI is every single one of these steps. Like, look at the final step here. There is some inference going on, because not writing exactly the tactics, not writing exactly, well, here you substitute this, here you apply precisely this thing. That's because, you know, like a human reading this proof will infer all these little details. And the Acorn prover will also infer all these little details. And if you want to see them, you can go to the assistant and see, okay, proving the goal, it uses lemma 3, it uses claim 3, you know, it uses the definition, and you can see all these steps for what it rewrites. This is ugly and it should be cleaned up, right? It shouldn't say magma mul. It should use the actual infix operator. Yeah, I should make a to-do for that. But anyway, this is how it works. If you're curious, definitely check it out. Overall, we don't have anywhere near the depth of math library that I'd like to have. We're still working on basic stuff around real numbers, complex numbers, and that'll make it possible for us to compare on benchmarks like mini F2F and Putnam bench, things like that, because right now we just can't express stuff. So this thing is convenient because for a magma, you really just only need to say, hey, this is a type that has one operation, and then we prove one thing about it. So it's a really good way to check out what a new theorem prover can do. Yeah, anyway, take a look. Thanks.